Okay, welcome everyone. It's my great pleasure to introduce Enrico Fatighenti from Rome, and Enrico will explain us how to look at the Fano varieties inside homogeneous vector bundles. Yeah. Thank you, Enrico.
Okay. So thanks, Mania, for inviting me. It's a great pleasure actually to be speaking at Zag's seminar. It's one of the seminars which I've been following with great pleasure for the past year. And I hope that it will continue for quite a long time. Anyway, so and I have to say that I cannot currently see the chat. I can see people, which is a great improvement. I've just learned how to do that. So if anyone is asking any question on the chat, could you please tell me, and I would be very happy to answer them. Okay, so what I'm talking about, it's a mixture of various projects which I've been working on for the past maybe 1 or 2 years with various people, and I will try to give credit to all of them at the appropriate time. Okay, so let me start with a definition which is super well known. So the definition of a Fano variety. So for me, a Fano variety in this talk is going to be a smooth projective variety such that it's anti-canonical example. And actually the purpose for me giving right now this definition is to highlight the fact that only for the purpose of this talk, I'm not going to consider Fano with singularities. Okay, so only for smooth Fano unless I say otherwise. Okay, and if we restrict to this particular choice, we have a very important feature of Fano variety, which is their boundedness. And this is a well-known property, and it simply means that if we fix any dimension, then for any fixed dimension, we have a finite number of deformation family of Fano varieties, so Fano varieties up to deformation. And so, of course, like the step 0 of anyone who works in Fano varieties, they attempt or they decide to classify them. Okay, and we do have, actually, we know that they are bounded because we do know an explicit bound for the number of Fano varieties, but this bound is hugely not sharp. Okay, so for example, if you take this bound, which is, for example, a function dimension, and you plug in dimension 1 into this formula, you get that there should be up to 3 to the power of 18 Fano varieties of dimension 1. But on the other hand, we know very well that we have only one Fano variety in dimension 1, which is RSP1. And if we move to dimension 2, this is very classical. And we have 10 families of the Fano surfaces, or as they commonly known, del pezzo surfaces. And in particular, you can take P1 cross P1, or you could take P2, and you could blow it up in up to 8 points whenever these are in a sufficiently general position. Okay. And if we move to dimension 3, we do have 105 families, and classification is being done by many people, Fano itself, and then later on Iskowski and Mori Mukai. And I always like them to subdivide in 17 plus 88 according to their Picard rank. So 17 are prime. In particular, this means that the Picard rank is equal to 1, and 88 are non-prime, so the Picard rank is higher. And the reason for me proposing this subdivision is that the classification methods are very different a priori for the 17.1 and the 18. And then if we go to dimension 4 and higher, well, the classification is not known. Some, or maybe many examples are known. For example, I've checked, and if we put all the various databases together, we can find around 700 families of Fano varieties known in dimension 4, but still, classification is quite far away. And what, sometimes is done, and I find it very useful, is to refine the classification using another invariant of a Fano variety, which is the index, okay? And this is another very famous invariant, which is simply the greatest integer of the divisibility of the anti-canonical class in the Picard group, okay? So an important result is that, again, for a smooth Fano variety of dimension n, the index is bounded by the dimension +1. And in fact, this happens if and only if X is the n-dimensional projective space. And if we take the index 1 less, so index n equal to the dimension, then X can be only the quadric hypersurface, smooth quadric hypersurface. And we can lower a little bit the index again. And so we can take the index equal to the dimension -1, and we have a fully classified list of Fano variety in any dimension. And these are called del pezzo manifold because they're quite similar to the del pezzo surfaces, in fact. the higher dimensional generalization. And then we have some other partial result. For example, we could take the index equal to n-2, and we could assume that the pK rank is equal to 1. And then once again, we have a finite list of classified Fano varieties. They're called Mukai manifold. And you can see that in the last line of this list of items, another partial result when the index is higher and the pK rank is higher, etc., etc. This time by Wisniewski. Okay, so basically, as we can see, the first remaining case is the first case we want to consider, the first case of interest, if you want, is for Fano fourfolds of index equal to 1. And in fact, this project, which I'm going to report on, has 3 main aims. The first one is actually to produce many new examples, or maybe as many as possible, in dimension 4 or index 1. The second, which I find very nice and intriguing, is to, in some sense, establish a dictionary between, in some sense, a biregular list of examples that you're able to produce and the birational Mori-Mukai style language. More on that later. And finally, kind of an offspring of this project, to construct Fano in very high dimension with special Hodge theoretical properties, and link with the hyperkähler geometry, which is another story we're going to talk about later. Okay, so which kind of Fano do we want to produce? Which kind of Fano do we want to work with? Basically, our tool of choice to explore in the landscape is to construct Fano varieties. How? Basically, a zero loci of sections of homogeneous vector bundle over homogeneous variety. So in general, I will do a lot of examples. So if you're not familiar with it, don't worry, I will tell you everything. But if you want a proper definition, we would be required to start with a Lie group G, together with some gadget. So for example, connected, simply connected, complex, semi-simple, etc., etc. A parabolic subgroup P, and a vector bundle E on G mod P, which is homogeneous, and it means that it's isomorphic to this G fiber product. So if you're not familiar with it, you should just consider this typical example, which is going to be like probably the most relevant example for this talk, and you just take as G mod P the Grassmannian of K subspace, K dimensional subspace in an n-dimensional complex vector space. Okay, and then of course we all know that the Grassmannian came with 2 distinguished vector bundles: the rank K tautological, which I will denote by U, and the rank n-K quotient, which I will denote by Q. And then you can take as an example of such vector bundle a direct sum of Schur functors applied to U and to Q. Okay, so for example, this means that we can take symmetric power, exterior power, and other more complicated combinatorial objects. Okay, so why should we be interested in working with this type of Fano varieties? Well, I do see 3 main advantages. There might be more, of course. The first one is that in this way, we can, in fact, produce a lot of examples. And this is already a very good thing if one is interested in understanding the geometry of higher dimensional Fano. The second, which is probably the biggest advantage of this method, is that the classification of Fano of this type, and I stress of this type, can be reduced to a combinatorial problem. And combinatorial, of course, does not mean easy in general, but we do have some more tools to address it. And finally, it's definitely easy to compute meaningful invariants of the Fano varieties, for example, Hodge numbers, using, for example, Borel-Bott-Weil theorem, Koszul complex, and other standard tools in representation theory. Okay, so in the next slide, I'm going to do a lot of examples, but maybe the example 0 of varieties defined this type is that all complete intersections are, in fact, examples of this type. But of course, there are much more. Okay, so let me give you an inspiration, because we didn't come up with this idea, but in fact our inspiration was Mukai's classification of prime Fano threefolds. And as I told you, there are 17 families of prime Fano threefolds, and 7 of them, in fact, have an index greater than 1. And all of them, except V5, which I'm going to define, in fact, are complete intersection in a projective space, possibly weighted. And if you take the other 10, which have index 1, so as you probably know, they are labeled by a number, the genius, which is a number going from 2 to 12, excluding 11. we have the G for genus 2, 3, 4, and 5. These Fano are in fact once again complete intersection in the weighted projective space, possibly weighted. But the remaining, to describe the remaining them, we do have to use this language. And in fact, the remaining Fano have a nice description in this way. And I'm gonna pause 1 second to to point you out this definition. So from this point on, whenever I'm writing x equal to g comma f, what I will mean is that basically x, the general x, is going to be given by the zero locus of a general section of a vector bundle f, which is a vector bundle over some variety g. Okay, so this is the list of the other Mukai Fano threefolds, and as we see, we have v5, which has index 2 and degree 5. And its classical model, we all know that we can describe it by taking Grassmannian 2,5 and cutting it with 3 hyperplane section. And in our language, we would write as G equal Grassmannian 2,5 and as vector bundle 3 copy of 1. And in fact, this is not a complete intersection in a projective space, but in some sense, in a very definite sense, is a complete intersection in a Grassmannian. So in some sense, we have still a complete intersection lurking around. And maybe I'm not gonna read all of them, but suppose that for 1 second we look at the genus 9 example, okay? So if you look at the genus 9 example, degree 16, our ambient space is Grassmannian 3,6, and then the vector bundle, we could take 1 copy of wedge 2 of the dual of the tautological bundle and 3 hyperplane section. And this a priori is not a complete intersection, but in fact, the first bundle, so the rank 3 vector bundle, which is given by the wedge 2 of U, cut the Lagrangian Grassmannian 3,6 inside the Grassmannian 3,6. And so we have 3 extra hyperplane section. So in some sense, this is still a complete intersection in a Lagrangian Grassmannian. But the last one, degree 22 and genus 12, it's kind of different from all the other, and in fact can be described by taking Grassmannian 3,7 as ambient space, and then we have this rank 9 vector bundle, which is 3 copies of the wedge 2. And in fact, this is not a complete intersection anywhere else. And this variety is sometimes called the 3-symplectic Grassmannian. Okay, so this is just to say that this language has, it's really relevant for if one has to classify or at least understand Fano varieties in a dimension. And so we do have, in fact, a very natural question, which I started asking myself like maybe 1 year ago or something, is that do we obtain all already classified Fano varieties in this way? So using this language, can we describe all Fano varieties? And the answer is yes. So this is very classical in dimension 1 and 2. And in dimension 3, so the case of a non-prime Fano threefold, so pick a rank 1, as I told you, we had 88 cases left. And if we look at the original classification, this was done by Mori Mukai using Mori theory, and it's a wonderful classification. Of course, it's very famous, but it's done in birational terms, which is not really this language. And in particular, in most cases, they're described in terms of blow up of curves of points in other Fano of lower picker rank. And in fact, this classification is a little bit harder. Actually, it's quite hard to generalize in higher dimension. And then if we do a little time jump and we get to 2013, Coates, Corti, Galkin, and Kashprik, we're able to rewrite Mori Mukai classification. And basically, they were able to describe all Fano threefold as zero loci in some GIT quotient. And their aim was to compute the quantum periods. And this is a fancy language, but in many cases, and this was kind of the point of their paper, their model of choice was in fact a complete intersection in a toric variety. And in some sense, we wanted to see if we could somehow complete the picture. So in some sense, we wanted to find the most general language to describe all of them. And if you attempt to do such a task, there are multiple ways of doing that, and this is how we did it. So the first step is to, in fact, run a search, maybe I should say a computer-based search, to enumerate all possible Fano threefolds that can be defined in this way, so as G comma F, and then you want that, you take this minus should be in front of everything, so KG times determinant of F. So if you restrict this guy, it will give you the anti-canonical de Fano, but you want this bundle to be already ample on G. And the second step, you want to compute the invariants, for example, the anti-canonical section, the volume, the Hodge numbers, many others if you want. And you want to match each couple GF that you find in step 1 with a candidate in the Mori-Mukai list. And this is kind of automatic. And finally, what I did find most interesting and challenging is to in fact prove a series of basically lemon results that allow you some sort of dictionary that allow you to translate the biregular language in the birational language and vice versa. And this is, I think, the core of the idea, because you just don't want a list, you want to be able to understand this list, both from the biregular point of view and from the birational point of view, and to pass seamlessly from one case to another. And in fact, last year we did this theorem in collaboration with De Biase and Tanturri. And we did obtain all 105 families of Fano threefold, and we have a description for all of them, so as couple F comma G. And we required F to be homogeneous and G only a product of Grassmannians. Okay. So let me give you a couple of examples. So let me consider, for example, the Fano 216. So when I say 216, this is in the original Mori-Mukai notation, and 2 simply means that this guy will have picker rank equal 2, and 16 it means that he's the 16th Fano with that picker rank 2. And if you look through the original birational description given by Mori-Mukai, what you have to do, you have to take the complete intersection of 2 quadrics in P5, and then you have to blow up this complete intersection of 2 quadrics in P5 in an extra conic C, which is contained in this complete intersection. And in fact, you should notice that this conic is not a complete intersection in the quadrics themselves. Okay, and in order to perform our description, you take as ambient variety a quite simple variety. So you take P2 times the Grassmannian 2,4, which in fact is a quadric in P5. And then you take this very simple vector bundle. So you take another quadric, which is only on the Grassmannian 2,4. This is just a simple line bundle. And then you want to take the rank 2 tautological bundle on G24, and you want to twist it by the O1 on P2. Okay. And the interesting part is actually to prove that this birational and this biregular description agrees for all elements, for all Fano in these families. And then maybe I could do another example, because the Mori-Mukai description as when the picker rank increase tends to be more and more complicated. So let's take, for example, the number 4, the 4-4. And if we take the birational description, what you should do is you should take a 3-dimensional quadric. Okay, you should blow it up in 2 points, and then you should blow it up again in the proper transform of a conic through the points. And our description, in fact, is quite simple. So as an ambient space, you take P1 cross P2 cross P4, so a very simple variety. And then you take 2 line bundles, so of degree 110 and 002, and then a rank 2 vector bundle, which is given by the rank 2 quotient bundle on P2, and you want to twist it by O1 on P4. And more or less, this is how it goes. So for any birational family, you find the equivalent described with the zero loci of vector bundles. Okay, so this is all very nice and very good for Fano threefolds. And but then we decided to attack the higher dimensional case, which in some sense was our objective from the beginning. Okay. The problem is, in some sense, that if you want to attack the higher dimensional case, at least we wanted to start from some assumption in order to simplify our lives. And so let me begin with a definition for you. Okay, so suppose that we have a Fano, once again, smooth projective Fano, and suppose that you can obtain your Fano in as G comma F. So in our language, in our model. And then we say that X admits a strongly reducible, and we abbreviate it as SR, Fano model, if these 2 following conditions are satisfied. So the first one, you want the vector bundle F to be completely reducible. G has to be homogeneous, of course, here. And the second condition, I already hinted to you before, you want that basically you take the dual of the canonical of G times the determinant of F, and you want this to be already ample on G, okay? And this is basically a working definition which allow us to, in fact, it simplifies a lot our life for various reasons. But you know, you should ask me, or I should tell you, how restrictive is this subdefinition? Or if you want, how many Fano that we know of admit models as SR Fano model, okay? And well, the answer is a positive one. So this means that this definition is not too restrictive. And in particular, if you go to the Delpezzo surface, 9 out of 10 that we know of admits model as strongly reducible Fano, so as SR Fano. And if you go to dimension 3, in fact, 85 out of 105 admits such description. And in general, we do expect that a substantial percentage of all Fano admits such model. Okay. And yes, well, I mean, the main reason why we are interested in asking for this definition is that SR Fano can be quite easily, or at least more easily, classified, for example, by means of computer algebra. And we did identify 2 cases to our liking, which are the cases we decided to focus on. And the first one is SR Fano fourfolds of index 1. And the second one is SR Fano varieties of K3 and Calabi-Yau type. Okay. And maybe I should mention that it's easy to, I mean, it's possible, it's quite easy in some sense to understand if a Fano variety admits as SR model, but it's quite hard to prove, or at least I don't know how to do it, to prove that a Fano varieties cannot admit such a model. So when I say that, for example, 85 out of 105 in dimension 3 admits such model, it means that we don't know how to produce such a model for the rest of them. So I've discussed about Fano fourfolds, and I will be back on Fano fourfolds in a couple of slides. But since I mentioned in the previous slide Fano varieties of K3 type, I just want to give you a definition and do a little detour in order to introduce you this type of Fano varieties. So let me start from, in general, smooth and projective variety X. And suppose you want to take its J cohomology group already in its Hodge decomposition. And you see that this J cohomology group, so HJ, is of K3 type if these 2 following conditions are satisfied. So first, the first condition you want to ask is that HJ is of Hodge level 2. And so it means that all the group in the Hodge decomposition are 0 except 3. And the second condition is that the first and the last dimension in this 3 surviving vector space is 1. Okay. And then we say that a Fano variety is called a Fano variety of K3 type, or if you want FK3, if there exists at least a J such that HJ is of K3 type. Okay. So this can be a quite technical definition in some sense if you've never seen it. So let me give you a typical example. Probably I would say example 0 if you want. It's a quite famous one, in fact. And suppose you start from, you take a smooth cubic fourfold. So in our notation, you take P5 and O3, okay? And suppose you write down its Hodge diamond, and I did write only half of it because of space reason. Then you can see that in H4, which is in this case, the central line, you do have a Hodge structure which starts with, you know, of course, 0 because it's a Fano variety. And then the 3 central term are 1, 21, and 1. And of course, if you're into numerology, you might recognize some sort of similarity with the numerology of a K3 surface. And in fact, this is not a coincidence. And there is a beautiful story trying to relate the supposed irrationality of the cubic fourfold together with the presence or not of a geometrical K3 in some sense. Okay. And another example, which in fact is going to be quite relevant later on, is suppose you want to start from 20-dimensional hypersurface in the Grassmannian 310. Okay, so Grassmannian 310 is a Grassmannian of dimension 21, and then you take an hyperplane in its Plucher embedding. So it's given by a 3-form, a skew symmetric 3-form in 10 variables. And I didn't draw it Hodge diamond because of space reason, but you could very well see that this is a Fano variety of dimension 20 with a K3 structure exactly in H20. So once again, in the middle cohomology. Okay. I mean, one question that you might very well ask, which it should be quite relevant up to this point, is why are these varieties interesting? Okay. And in fact, our main motivation lies in the study of another class of varieties, which a priori is very different from Fano varieties, and they are called IHS, or irreducible holomorphic symplectic, or hyperkähler, depending who you ask to. And if you don't know the definition, these varieties are in fact simply connected, and you want that the space of global holomorphic 2 form is one-dimensional and generated by non-degenerate symplectic form. Okay, so these are very different from Fano varieties in particular. So in particular, for example, they have codere dimension equal to 0. And actually, unlike Fano varieties, it is not clear if there is a sort of boundedness result or not about this hyperkähler variety, but examples are in fact extremely rare. And up to now, we have 2 classes in any dimension discovered by Bouville, maybe around 35 years ago, and 2 sporadic classes in dimension 6 and 10, understood by Kirano Gredi, maybe around 20 years ago. Okay. Right. So what is the idea? The idea behind this, some sort of bridge between these 2 words, is that we do have a very well, we do want to be able to, and we expect to be able to do it, to associate to any family of Fano variety of K3 type many examples of IHS. And this can be of different degree, dimension, and in fact, even deformation type. Okay. But the moral of the story is Fano varieties, even of K3 type, are in general easier to find, or easier to hunt if you want, than IHS. So in some sense, we could be interested in understanding Fano varieties with special Hodge theoretical properties to look for new examples or new example of polarized families of IHS. And for example, suppose we start from the cubic fourfold. I was describing it to you before. And from the cubic fourfold, you in fact can associate a lot of different hyperkähler of various type and dimension and everything. But let me mention first the most classical one, which is a result very classical by Bouville and Donaghy in the 80s. So to a smooth cubic fourfold, you do associate its variety of line, so the variety parameterizing lines on it, which is a subvarieties of the Grassmannian 2-6. And in fact, this happened to be an IHS fourfold, which is the formation equivalent to the Hilbert squares, so the Hilbert schemes of 2 point on a K3 surface of genus 8. And the interesting stuff is that you can in fact describe this variety of line in our language. So in Grassmannian 2-6 as ambient varieties, and then you take the 0 loci of a section of this vector bundle. So the third symmetric power of the dual of the tautological and the Grassmannian. Okay, and even the other example, which I briefly mentioned to you before, so the hypersurface in Grassmannian 310 has an hyperkähler associated. In fact, in this case, I do believe that we have only up to now hyperkähler associated. And this one still parameterizes a space of special subvarieties, and in particular, it parameterizes the space of Grassmannian 3-6 contained in this special Fano. And it turns out that this set, this hyperkähler fourfold, is once again the formation equivalent to the Hilbert squares of 2 point on a K3, but this time the genus is different, so genus 12. And once again, you can describe Z in our language. So you take as ambient space the Grassmannian 610, and you take as vector bundle this wedge 3 of the tautological. Okay. So I've told you about Fano fourfolds of index 1. I've told you about Fano of K3 type, and let me now try to summarize our current progresses on both of these 2 topics, and in particular in the intersection of these 2 topics. So let me start with a report on a project which is currently ongoing together with Marcello Bernardana, Laurent Manivelle, and Fabio Tanturri, which is to classify or at least understand the SR Fano fourfold of index 1. Okay. In fact, we do currently have around 800 families. The database are updating themselves, so this number might be a little different in a while. So 800 families of index 1 Fano fourfold that admits SR models, okay? And of course, we will have to cross-check this data with the existing database to see how many new examples we have in our list. But just judging using the numerology, we are quite optimistic that quite a number of interesting new families of Fano varieties are there. And in fact, our purpose, or what we want to achieve, is a Mori-Mukai style classification in this very specific subcase. So our aim is not only to have a huge list, but to be able to understand them, and in particular, being able to understand them and the rationality properties. And let me give you an example to basically show you what I'm talking about, more or less. So suppose you take the Fano Y, which is cut in P2 cross P5, by this rank 3 vector bundle. So you take O11, so the line O1 on both components, and then you take the quotient bundle on P2, so rank 2, twisted by O2 on P5. And suppose that you are able to compute invariance using the usual Hodge theoretical package. And so you understand that you have a certain number of canonical sections, you understand the volume, and you understand this Hodge structure. So what we want to understand is what are these varieties in general, and we did describe this guy here basically as the blow-up of a cubic fourfold in a general K3 surface of degree 8. So of course, a cubic fourfold containing a K3 surface of degree 8 cannot be general. So in fact, it is Hodge special, but we can show that it is general in C8, which is the divisor of cubic fourfolds containing a plane. And in particular, we do expect that this Y is not expected to be rational. And so what we want to do is understand all this Fano in this way, and more or less the network of blow-ups, blow-down, and other bilateral maps between them. Right. So we have this huge list of more or less 800 or something Fano fourfolds, and how many of them are Fano K3, Fano fourfolds of K3 type? So before telling you, the numerology, let me remind you that we do have a bunch of other FK3 fourfolds which are known in the literature, okay? And in fact, only 3 of them are prime, so their pK rank is equal to 1, and they all have either an actual or conjectural IHS which is linked to it. So the first one, of course, not of index 1, but you do have the cubic fourfold. We already discussed about this. And then another one, which is quite famous and quite well known, it is the Gushel-Mukai fourfold. So what you do is you start from the Grassmannian 2,5, and you want to cut it with an hyperplane and a quadric, so O1 plus O2. And in fact, there is a beautiful theory, there are beautiful mathematics beyond this Fano fourfold, and actually a series of very recent work, old and very recent work at the same time. And you can associate an IHS using Lagrangian data. And there are many, many people who did beautiful mathematics on this topic. And let me mention briefly, for example, Iliev and Manivel or the Baron-Kuznetsov, but once again, many, many people involved in this. And then there is a third example, which is a bit more mysterious, and it's called the C5 fourfold. And it has, this is a fourfold which has been studied by Kushlev in mid-90s first. This one is a bit more mysterious. Even the description is quite complicated if you compare with the other two. And so you start from the Grassmannian 37, and what you do is you cut the Grassmannian 37 with this, which is a 12-dimensional variety, and you cut it with this rank 8 vector bundle. So we do have a copies of wedge 2 of the dual of the tautological, and then we have a twisted quotient the dual of the distant quotient bundle, and then an hyperplane class. And in fact, an IHS linked to this guy, to this Kushlev fourfold, has been long conjectured, possibly via the Hilbert schemes of twisted cubic containing this Fano. But as of today, no one has been able to do this. But still, it is a long conjecture. And in fact, a curious coincidence, if you like the right categories, which I do. is that both the cubic fourfold and the Gushel-Mukai fourfold, you can very well write the semi-orthogonal decomposition and understand the Kutzenstoff component, for example. But a full exceptional collection for the fivefold, which you take by not considering the hyperplane section on the C5, has not been found yet. So in some sense, there is this analogy with the F category role. Okay. And then there is another Fano K3-fold, which is done in the literature. It's called Derra fourfold, but it should not admit an SR model. In fact, it is described as a double cover of P2 cross P2 ramified in a divisor of by degree 2, 2. So what about non-prime Fano fourfolds? And this is part of a work which is slowly converging to its completion, and together with Manibel, Bernardin, and Tenturri, and we should be able, hopefully, to finish it in a few months, not too long. And so in our list of SR Fano fourfolds, we wanted to isolate all of them which are Fano variety of K3 type. And in fact, we did find 64 of them. And we believe that in some sense, they are conjecturally complete. And this simply means that we cannot find other FK3 fourfold using this SR language. And we are almost done describing all of them. And in fact, we do have a description of a complete description of 53 out of 64. And the remaining one, we still understand them to some extent as of today. And just to give you a kind of description of these 53 families, we do have 16 of them, which can be, in fact, realized as blow-up of a cubic fourfold, which is possibly Hodge special. 5 of them are rational. The other, of course, we don't know. Otherwise, that would be too interesting and too strong, possibly. And 5 of them can be realized as the blow-up of a Gushel-Mukai fourfold, once again, possibly Hodge special. 35 of them can be realized as blow-up of, I'm saying central variety, but what I should really say is variety with Hodge level less equal than 1 in a K3 surface. And out of that, 33 we know to be rational. And in fact, finally, we do have 3 of them that do not fall in any of the previous category, but in some sense, we can still relate them to either K3 surface or cubic fourfolds. Okay, so basically this work in which we will describe all their birational properties should be hopefully out soon, and I hope to be able to talk about it in a subsequent work one day. So actually, in fact, just studying the list which I've been mentioning to you, we can formulate a conjecture. Because if we go back for 1 second to this slide, you see that basically all these 64 families of Fano K3 have a K3 Hodge structure, which is somehow old, or in some sense already explained by something that we know. So let me formulate a conjecture. And to do that, suppose that we have a Fano K3 fourfold, and suppose that we write down its Hodge decomposition, so its Hodge structure, as a direct sum of a certain A1 of AB of X and its complement, and we denote by AV or A vanishing of X, basically the K3 substructure intersected with the vanishing homology of X. So this is just, we take the homology of X and we throw away everything coming, every cycle coming from the ambient space. And we do have this conjecture, which up to now is just experimental. So suppose we have a Fano fourfold, a Fano K3 fourfold, FK3, and then we believe that this vanishing Hodge substructure has to be isomorphic to the vanishing component of the AJ of a certain Y. And then we think there exist only 2 possibilities. So either J is equal to 2 and Y in fact is an actual K3 surface, or J is equal to 4 and Y is either a cubic, a Gushel-Mukai, a C4, or a Derra fourfold. So in some sense, this means that even with our very loose definition of K3 substructure and Fano varieties of K3 type, we don't find anything too exotic, at least in the realm of fourfolds. Okay. And we can take, of course, this conjecture, and we can make it non-commutative. And if you can make it non-commutative, this very convoluted vanishing component of the Hodge structure of the K3 substructure has to be replaced with the by the Kuznetsov component of the derived category of X. Okay, but we didn't want to state this conjecture in a non-commutative way. First of all, because we wouldn't know how to address it properly in the C5 case. Okay. So what about in general higher dimensional K3? Higher dimensional Fano of K3 type? Do we expect, in fact, something similar? Because the problem is, or the point is, that what this conjecture is really saying is that once again, you don't have exotic Fano fourfold, exotic K3 type structure in Fano fourfolds. But maybe in higher dimension, the situation is different. Maybe in higher dimension, you find new exotic K3 structure. The problem is that in general, looking for Fano K3, even in this SR model, in arbitrary dimension is quite a difficult task, okay? But we know more or less how to use some tricks and strategies and so on and so forth. And I mean, this is my favorite one, but there are some more. So suppose you start from a Fano, which has a dimension to t+1, so odd dimension, and suppose that you have of certain index m, and you do want a divisibility condition between t, which is part of the dimension, and the index m. And suppose that the Hodge level of the middle cohomology of y is less equal than 1, and you have to require some extra vanishing conditions. Then what we will get is that the general element of this linear system, maybe I should say is MIMF, is in fact a Fano variety of K3 type. Okay. And so basically using these tricks and some other, we did have this work of a couple of years ago in collaboration with Mongardi that in some sense predates all the other results which I've been telling you in the past 40 minutes or something. Okay. So this theorem with Mongardi tells us that we do have 23 new families of Fano varieties of K3 type of dimension greater than 4, in particular of dimension which is included between 6 and 20, pick a rank between which is either 1 or 2 and 3, and the index which is close to half of the dimension. In fact, it is between the dimension over 2 and dimension over 2 minus 1. So I'm not going to tell you all these examples, but let me focus on some of them which we did believe that were the most interesting one. Okay. So for the first one, we should start from the Grassmannian 3-9, okay? And then as a vector bundle, we should take a copies of the wedge 2 of the dual of the tautological and an hyperplane section. And this is a Fano variety of dimension 14. It has index 6, 1 K3 structure in the middle cohomology. So of course, from the level at the level of linear algebra is defined by a 3 form in 9 variable skew and a 2 form in 9 variable skew. And in fact, this was already present in a work by Iliev and Manivel. Okay. Or then you could take another variety in Grassmannian 3-8, and this time you should take 2 section of this wedge 2. So you should go to the bisymplectic Grassmannian of 3 planes in an 8-dimensional vector space, and then you should cut with another hyperplane section. And so what you get is a 8-fold, so a priori very different, of index 3 and 1 K3 structure. Okay. And then another variety which is once again an 8-fold, once again of index 3, but this time this guy has 3 K3 structure in H6, H8, and H10. And this is given in the Grassmannian 210 by a 0 locus of this vector bundle, whose global section, in fact, are 3 skew forms in B10. And let me remind you that all these varieties are prime. So it's not possible, for example, that this guy here with a 3 K3 structure is the blow up or some other birational, easy birational transformation to another Fano K3 type. And or we could take this variety and we can take an hyperplane section of it, and then we could find, of course, 2K3 structure by simply the left-shade hyperplane theorem, and then one extra Tricalabiau structure in the middle cohomology, which is quite interesting. It's the first example of this type. Or another variety, which a priori does not admit an SR model, although I know how to describe it in some sense in a more complicated variety. So this is a very classical variety called the Peskin variety in P9. And in fact, this is a sixfold, once again of index 3. And once again, it has 3K3 structure in H4, S6, S8. And this is classically described as a degeneracy locus. In fact, as you can see, this varieties looks very different, for example, from the point of view of Hodge theory. Okay, so I basically draw a table with the non-trivial Hodge numbers of the above variety. So you can see, for example, starting from the left, this was the 8-fold cut by a linear section in the bisymplectic Grassmannian 3/8, and then you add the one in Grassmannian 2/10, etc., etc. So even visually, they're very, very different among each other. But then we had some sort of alarm, and the alarm started to sound when we saw that basically we were able to reconstruct, to associate to all this variety the same hyperkähler fourfold, which in fact is the de-Barboisian hyperkähler fourfold, the one already mentioned above, linked to the Grassmannian 3/10 and Grassmannian 6/10. And in fact, one is able to describe this de-Barboisian hyperkähler fourfold as parameter space for the copies of symplectic Grassmannian 3/6 contained in X. This is already contained in the original work by Iliev and Manivelle, or as the space of P1 to the third in Y, so this Y here, this by myself and Giovanni Mongardi, or as the space of some special rational fourfolds or threefold contained in T and P, and T once again is me and Giovanni, and P is Frederick Hahn. And you know, once this alarm bell started ringing, we wanted to understand if this variety, this Fano variety, which a priori were quite different among each other, were in fact related in some sense, right? Because it's not common that, you know, if you take 4 random or 5 random or whatever random Fano variety, which are very different among each other, they all maps to the same hyperkähler, considering how rare hyperkähler varieties are in general, right? And in fact, we did understand the similarities at the birational and Hodge theoretical level as well. But I'm quite sure that we wouldn't have noticed it without passing through the hyperkähler side. And what's the relation? So let me mention to you first the Hodge theoretical statement, and then I will explain to you the geometrical part. Okay. So what happens is that basically their Hodge structure is the single one. So we have the single master Hodge structure, which is the one coming from the linear section of Grassmannian 3/10, which I've been talking about before. And what you do is you take this master Hodge structure, and you spread it and you multiply it to all this variety through a very specific set of correspondences towards explicit X, Y, T, and P, which are naturally associated to W. So what you do is you start from W. Starting from W, it means that you specify skew symmetric 3 forms in 10 variables, and you have a natural way, only by the means, for example, of linear algebra, to associate the algebraic and geometric data corresponding to this X, Y, T, and P. And we are going to see in the next and final slide all this set of correspondences. But the theorem, which is part of a work of 1.5 years ago with Bernardara and Manivelle, is as follows. So suppose you take the 20-dimensional vanishing component of the cohomology of W. Okay, so what you do is you take the Hodge structure, the 20-dimensional Hodge structure of W, and you throw away 10 cycles, which are Schubert cycle coming from the Grassmannians. And then what we discovered is this K is in fact isomorphic to the 14-dimensional vanishing cohomology of X, 8-dimensional vanishing cohomology of I, and to the primitive cohomologies of T and P in the relevant degrees. So this is just a not theoretical statement to say what I've been telling you right now. So you do have this master of structure, you spread it, you multiply it, and you describe all their structures starting from this master one. And in fact, we do have a similar statement for the derived category as well. And as before, you do want the Kuznetsov component of the derived category of this 20-dimensional W that plays the role of the vanishing homology. And in fact, we can predict the shapes of the semi-orthogonal decomposition, and we can understand, we can conjecture who the exceptional object should be. But the problem is that you do have a huge number of exceptional objects, greater than 100 in some case, and so that's quite hard to prove. And so since I'm almost over, let me finish with the last slide, in which I want to comment on the set of maps and correspondence that we need to use in order to describe all this variety. So suppose you start from W, which you can find at the center of the picture, which is in fact the hyperplane section of Grassmannian 310. Okay, so let me start by describing the right-hand side of the diagram first. So what you do, first you blow up this W in some symplectic Grassmannian, okay? And this blow up is induced by the projection from Grassmannian 310 to the Grassmannian 39 once you restrict it to the hyperplane section, okay? And in fact, this is simply the resolution of the indeterminacy of this projection. And so basically what you realize is this blow up maps is generically a P2 bundle over the Grassmannian 39 itself, but it has a degeneracy. And in fact, degenerates into a P3 bundle over X, and X was the linear section of the symplectic Grassmannian 39. And so what do you have, in fact, is a stratified projective bundle. And the stratified projective bundle, you can use basically a little bit more complicated, but not too much, version of the blow-up formula or the Orlov formula for the derived category if you want, and you understand how to transfer this whole structure from W to X. And then you can do it once again. So you blow up once again in another symplectic Grassmannian, and this one project to the symplectic Grassmannian 38. And this is a P2 bundle generically, but once again degenerates into a P3 bundle on Y, which was the linear section of bisymplectic Grassmannian 38. And so you were able to pass from W to Y. And then you know, a very natural question would be, can you do it once more? Because if we would do it once more, we would get exactly to the K3 of genus 12 and degree 22. But the problem is that in order to do this projection, what you have to do is you have to do a special vector, and this special vector has to be in a general position with respect to the symplectic form, to the skew forms. And if you, when you try to do the third projection, you see that you cannot choose this vector and keep Y singular. So you have, smooth. So you have to go through a specific degeneration of Y, and so the situation is not as easy as it is. And let me finish by describing the left-hand side of the diagram, which is a little bit different. So first of all, what you do is you go from W to what is Q star W? Well, you should imagine that above Grassmannian 310, you do have flag 2, 310. So the flag varieties of 2 spaces containing 3 spaces containing V10. So you can pull back this W, and in fact, this is a P2 bundle. And of course, we know that flag variety, 2 steps flag varieties come with 2 projection. So the other projection is to Grassmannian 210. And when you restrict it to this Q star W, this is once again a stratified projective bundle. So you have a P6 that degenerate into a P7, exactly over T. But this time you have a P6 degenerate into P7 that maintain one notch structure, but you have one P2 bundle that in fact explain why you do have 3-Hodge structure of Q3 type. And in fact, you can do more or less the similar thing with, you can do once again more, passing through the flag 1 to 10. And what you get is that this Q star T, which is a P1 bundle over T, it's a blow up of P9 with center this Peskin variety that we were discussing it before. And so you do explain as well the Hodge structure to this Peskin variety. And so let me just finish. Let me just mention that in this theorem that I told you and this construction, basically told you that if we go in higher dimension, up to now, we do have the K3 structure in the fourfold case, and one extra K3 structure, which is the one coming from this hyperplansection of Grassmannian 310. And of course, the very natural question is, do we have new genuine K3 structure lurking around? And well, the honest answer is, I don't know. I think there are. I have some ideas on where to look for them, and et cetera, but up to now, it's just wishful thinking. And but I do hope to be able to find them at some point. And that was the last slide. So thanks for the attention, and thanks for listening.
Thank you, Enrico. Thank you very much for beautiful talk. Let's think also in Zoom like this. Okay, thank you. Questions? Please ask questions. I have question regarding the first part of your talk.
Yes, please.
Yeah, for example, just for the practical issue, like for application. So, for example, Alessio needed this description of Fano's basically for the for the mirror, yeah, just to compute.
Yes.
So your description, can you, for example, use it to some, for example, to compute automorphism group of Fanos or something like this? So some applications of basically
yes.
representations. At least
in fact, this is one. No, but in fact, this is an excellent question, and in fact, this is one of the first applications that I have in mind. So we, for example, already in the threefold case, we did a work a couple of months ago together with Peter Bellmans and Fabio Tanturri, in which we did not describe the automorphism, which are already well known for the Fano threefold case, but we did describe the section of the wedge 2 of the tangent power, which in some sense are a higher dimensional generalization of automorphism. And we did use our methods. And the upshot is that the moment you're able to have a description, to use such a description for this Fano variety, in fact, you can use this to understand automorphism. And in the fourfold case, for example, that's already an interesting one. But let me say that in general, what we are really interested in is both understanding automorphism in higher dimension and more generally understanding birational links between all these Fano. Because this is, I mean, we do have some sort of dictionary between these two languages, and this is all very systematic, okay? So the moment you understand how to pass between one each other, you can do it for all of them. So this...
I actually disagree with that. You said that automorphism is well known, because connected component is well known, and connected component, they basically preserve every birational construction. So to find them, you actually don't need a delicate description like you have. But your description can be used to describe automorphism, which actually permutes extremal rays, so it's kind of more delicate.
In fact, you're right, because I said well known, but what I meant is the out zero. In fact, that's the one I was thinking.
Out zero, yeah.
Of course, you know more. It's it's a rule. So. But okay, yeah, no, definitely.
Okay, good. This is good. Any other questions? Let's just see. There's no question in the chat. Okay. If there are no more questions to Enrico, let's thank Enrico again. Thank you very much. Yeah, and okay, I stop recording. I will upload.